Welcome to the session. Today we are going to discuss permutation groups and cosets. So here, what is meant by a permutation? Permutation group. Before that, we have to know what is meant by a permutation. So permutation is nothing but a function. Permutation is nothing but a function. Let us, if you are going to consider P is a permutation, P is a function from A to A. A is a set. Let us assume that A is a set which is consisting the elements A1, A2 and so on AN. And so on AN. P is a function from A to itself. If P is 1, 1 and onto function, that is, if P is a bisection, then it is known as a permutation function. Then it is known as a permutation function. Say, let us assume that we are going to take A is mapped to A1 is mapped to P of A1. A2 is mapped to P of A2. And so on. AN is mapped to P of AN. P of AN. So this is, we are calling it as a permutation function. Now, this permutation function, we are going to represent it in two-line notation as, we have to consider this as like this. So here, this is A1, A2, these are all the elements of A, and the corresponding images are P of A1, P of A2, and so on, P of AN. P of AN. AN is mapped to P of A1, A2 is mapped to P of A2, and so on, AN is mapped to P of AN. P of AN. This we are going to represent a permutation function in a two-way notation. This is going to be written as a two-line notation. Two-line notation is going to be represented like this. So here, a permutation group is nothing but a non-empty set, which is what we are saying that when we are saying that G is a group, G is a non-empty set. G is a non-empty set. Set of all elements, whatever the elements will be there. So it is a real number system, or it is a natural number system, or it is a some other system. So G is a non-empty set. Now here, permutation group means it is consisting all permutation functions. All permutation functions. What is meant by all permutation function? Suppose if I am going to take, let us take A is equals to 1, 2, 3 set. A is 1, 2, 3 set we are considering. Then the permutation we are going to represent, let us say, the initial permutation function as it is consisting 3 elements. So we are going to get 3 factorial functions, permutation functions. That is nothing but 6 functions. What are those 6 functions? So we are going to represent it as 1, 2, 3, 1, 2, 3. So it is 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. So this is nothing but the identity function. And let us consider the another one is P1 is the first row, which is nothing but the set of elements. Second row, which are nothing but the images. Let us say 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. And next P2, let us, I am going to consider this is 1, 2, 3, and the images, 1 image is 3, and 2 image is 1, and 3 image is 2. Let us consider another set P3, which are going to take as first line is nothing but the set of elements of A, and 3, 1, 2 is already over. Now 1, 3, 2. I am just considering 1, 3, 2. This is another set, and P4 is once again 1, 2, 3 and 3, 2, 1, and P5 is let us have 1, 2, 3 and next 2, 1, 3. So these are all permutation functions. Suppose possible permutation functions if A is consisting only 3 elements. And here A is consisting n elements, then the permutation functions are n factorial in number. So G is a set of permutation functions. So it is nothing but P1, P0, P1 and so on, P5. So this collection, and next a binary operation. Let us consider the binary operation is composition. If we are going to prove G is a non-empty set of permutation function and the binary operation is composition, then if G satisfies all the group properties, then that is known as a permutation group. So here we have to verify what about the product of two permutation functions. We are taking P0 is the identity function. If we are going to multiply with P0 with any number, so I am going to take it as P0 composition with P1 is P1, P0 composition with P2 is P2, and so on. P0 composition with P5 is also P5 because the P0 is an identity function. Suppose if I am going to consider P0 circle P2, let us say. So P0 is 1, P1 is 1, 2, 3 and 2, 3, 1. Let us assume that I am just last one. See here what is the P1 is? P1 is this one. We have to consider that. So 2, 3, 1, 2, 3, 1 and the composition is P2. What about P2? Once again, this one we have to take 1, 2, 3, 3, 1, 2. So it is 1, 2, 3 and then 3, 1, 2. The composition, while we are going to calculate the composition, so it is 1, 2, 3 will be there, and next 1 is mapped to reverse. We are going to move. 1 is mapped to 3, 3 is mapped to 1, so it is 1 to 1, and 2 is mapped to 1, 1 is mapped to 2, and 3 is mapped to 2, 2 is mapped to 3. So I am going to get this one. So P1, P2, P1 composition with P2, which is nothing but the identity element, so which is a identity permutation, which is a P0. So like that, if I am just taking P1's composition with P3, so it is nothing but 1, 2, 3 and so P3 has 1, 2, 3. What about P3? See here it is a P3 is a 1, 3, 2. So 1, 3, 2. Then this is 1, 2, 3, 1 to 1, 1 to 2. So I am getting 2. 2 to 3, 3 to 1. So I am getting this one. 3 to 2, 2 to 3. So the product is I am getting like this. So this is the composition of P1 and P3. 2, 1, 3 will be there, which is equal to 2, 1, 3 is P5. So this I am going to take it as P5. So similarly, P1 composition with P4, just I am going to take it as 1, 2, 3, then 2, 3, 1, and then composition of P4. P4 is 1, 2, 3, and next 3, 2, 1. Then this is this is P4 is a 3, 2, 1. So then which is equals to 1, 2, 3, then 1 to 3, 3 to 1, 2 to 2, and 2 to 3, and 3 to 1, 1 to 3. So I am just getting this. What about this 1, 3, 2? So 1, 3, 2 is, see what about 1, 3, 2 is a P3. So it is nothing but P3. So this is the way that we have to multiply two permutation functions. Suppose if you are going to write the inverse of permutation function, so here what is the P1 is? P1 is 1 to 2 and the next 2 to 3 and the next 3 1. It is a P1 permutation function P1, and then P1 inverse is just reverse it. 2 is mapped to 1, 3 is mapped to 2, and 1 is mapped to 3. So this is a P inverse. This is a P inverse. If you are going to write into line notation, then is 1 is mapped to 3, 2 is mapped to 1, 3 is mapped to 2. So this is a P1 inverse. This is a P1 inverse. In such a way, we have to calculate the inverse of the permutation function, and the composition of the permutation functions are like this. Now, we have to verify. Let us assume that we have to verify if suppose S3, let us consider S3 as, I am just taking it as P0, whatever the permutation functions we discussed, or so all. So P1, P2 and so on, P5. P0, P2 and P1, P2 and so on, P5. And the binary operation is composition. We have to verify S3 comma circle is a group or not. So for that, we have to take it as the binary operation is, see here, the composition is the binary operation, and the set of all elements in S3 as P0, P1, P2, P3, P4 and P5. Next, another one. Here also the elements you have to write P0, P1, P2, P3, P4 and P5. Observe that we already here P0 is the identity function. If you are going to multiply with the identity function, any other function, we are going to get the function itself. So P0 circle P1 is P1, P0 circle P2 is P2, and P0 circle P3, P4 and P5. Now P0, P1. P1, P0. So it is nothing but P1, P1, P1. So what we are going to get P1, P1. So here in the same way we have to multiply P1 and P1. If I am going to take P1 circle P1, so it is a 1, then it is a 2, 3, then it is a 2, 3, 1, then circle 1, 2, 3, 2, 3, 1, then we are going to get 1, 2, 3, so 1 to 2, 2 to 3, so 1 to 2, 2 to 3, so 1 to 3, then 2 to 3, 3 to 1, then 3 to 1, 3 to 1, 1 to 2, so I am going to get this. So what about this P1, P3, 1, 2, 3, 1, 2, I am going to get it as 3, 1, 2 is P2. So I am going to write this as a P2. So now the same thing we are going to write it as a P2. Next, if I am going to write the another one is P1 circle P2. P1 circle P2 is already we calculated, it is a P0, so we have to write this as a P0. And the next P1 P3, P1 P3, it is nothing but P5. So I have to fill this P5. And the next another one is a P1 P4. So P1 P4 is P3. So I'm going to write it as a P3. Then P1 P5. In the same way, we are going to get it as a P4. And the next another one is P2 P0 is a P2. And another one is a P0. And another one is a P1. And another one is a P4. And another one is a P5. And another one is a P3. Then P3, if I am going to take P3, P4, then P5, then it is a P0, P1, P2, then this is a P4, P5. Similarly, you have to do all the things. So subsequently we are going to get like this. See, observe this is continuously we are going to get P naught. So P naught is nothing but, so simply we have to get here P3, then it is a P2, then it is a P naught, then it is a P1. Then another one is P5. This is a P5 and a P3, then it is a P4, then it is a P1, then it is a P2, then it is a P naught. See, observe, we have to get the composition table as like this. Composition table as like this. That means P5 circle P naught is P5 because P naught is the identity function. P5 P1 is P3, P5 P2 is P4, like this. So we are going to get the composition table is like this. So now, first of all, we have to verify whether it is closed or not. See, S3 under the binary opposition composition is closed or not. So closed means if you are going to take any two elements from this set and if you are going to apply binary operation, the resulting is also in the same set, then we are going to say it is a closed. Now observe here, all the elements, if you are going to consider any two permutation in any order, any two permutations in any order, then the composition we are going to get like this. We are going to get like this. And now all the elements are members in S3. All the elements are members in S3. So we can say that S3 star, S3, then the composition is closed. This is, we are just saying that it is closed. So the composition on the non-empty set S3 is closed. And associativeness, say composition of any three functions, if you are going to say, we are going to take, and the composition of three functions satisfies, our composition, our product of three functions, it is nothing but satisfies associative law. So it is automatically, associativeness is obvious result. Obvious results. Now what is the identity one? Associativeness is obvious. And now identity element, which is the identity element, is nothing but the identity function. Is nothing but the identity function. So here I am getting identity function P naught. P naught. We are going to have an identity function. So it is P naught is the identity element or identity function or is exist here. And next inverse. Next inverse. Suppose what about P1 inverse? P1 inverse. So where I am going to get P naught, then it is nothing but its inverse. So here where I am going to get P1, see here P1 inverse is P2. P1 circle P2 is P naught. So P1 inverse is P2 and P2 inverse is of course P1. Then P3 inverse is, see here P3 itself. And P4 inverse is P4 itself. And P5 inverse is and P5 itself. P5 itself. That means for each and every element, if I am going to consider from this set, it is obviously inverse element is exist. Inverse element is exist. That means inverse function is exist. So we can say that this is a group. This is a group. Now we have to verify whether it is an abelian group or not. We have to verify whether it is an abelian group or not. See here, whenever the composition of two function is not satisfies the commutative law. Suppose if I am going to consider P1 circle P5. What is P1 circle P5? It is nothing but P4. It is nothing but P4. What about P5 circle P1? P5 circle P1, which is equals to P3. So here composition is P1 circle P5 is not equals to P5 circle P1. So which is not an abelian group. This is only a group, and function composition is not satisfies the commutative law. So it is not a abelian group. This is only a group. Okay, so here S3 is consisting the identity element, and it is having a inverse of each and every element, and it is closed. So we can say that S3 is a group. S3 is a group. Now, so let us consider the another topic. So here permutation group. We are going to discuss a permutation group means G is a non-empty collection of permutation functions. Permutation functions. So if I am taking only a collection of few, that means G here I am just taking, which is nothing but P0, P1 and so on, P5 elements. P5. Each and every one is a permutation function. Suppose if it is having n number of functions, in the same way, it is also will become a group. It is also become a group under binary composition. Now let us go for the other concept. See the coset. So the other concept coset is, so let us say G be a group and H is a subgroup. G is a group and H is a subgroup under the same binary operation. Now let us consider A star H. For any element A, if I am considering from the group Z, then A star H is A star H such that H belongs to H. H belongs to H. We are going to call it as a left coset. We are going to call it as a left coset. That means whatever the elements are there in H, those elements we are going to apply the binary operation, whatever the binary operation will be there with the element of G. With the element of G, the set you are going to get, the set is nothing but the left coset. In the same way, because we are going to pre-multiply the elements of H with the element of Z, so it is nothing but a left coset. If I am going to apply post-multiplication, post-operation, then we are just reversing that. So it is nothing but a right coset, So here a coset means it is either left coset or right coset. Any one of these, we are going to call it as a coset. Now we are going to verify. Some of the examples. What is how we are going to measure the find out left coset and how we are going to find out the right coset. So now let us consider. So it is H is a integer set. Of course, any integer set which is a group under the binary operation plus. Now we have to consider a subset of this. This is Z, and we have to consider the subset is, this is nothing but a even integers, even or odd, whatever it is, even integers. So I am just taking, so obviously in the last classes we know that if E is a subset of Z, and if it is a group under the same binary operation plus, and we can say that it is also a group, conditions are satisfied, so we can say that it is a subgroup. So now if it is a subgroup, now we have to consider, see here the element, let us say A is the element, in Z. So whatever the binary operation that we are going to perform on group as well as the subgroup, the same binary operation that we have to consider. So that we have to take A plus E. So whatever the elements will be there, A I am just taking, this is the definition, this is the left coset. That means here plus operation we have to consider. If it is a product, if I am taking, then in A into I am going to get. So here plus, this is the definition. Then whatever the H is consisting, So what about E? That means E is consisting set of all even numbers, set of all even integers. So even integers means just multiply with 2. Whatever the n value will be there, whatever the n value will be there, whatever the n value, whether it is odd or even, then if you are going to multiply with 2, so subsequently we are going to get it is a even number. It is a even number. So here the elements of E are nothing but the even numbers. So we are going to take it as a 2n. Of course, it is having plus positive even numbers and a negative even numbers. So we are going to take plus or minus, and of course z is nothing but z plus. So if I am going to do all the things, so n is equals to 0, then I am going to get a, n is equals to 1, I am going to get a, this is a plus or minus 2, and n is equals to 2, a plus or minus 4, a plus or minus 6, and so on. So this is known as, if I am applying a, operation a, the post pre-operation we are going to multiply, we are going to apply, so it is known as a left coset. It is known as a left coset. And in the same way, right coset, so it is nothing but 2n plus or minus 2n plus a, plus or minus 2n plus a. So this is nothing but, just you have to take this is the, then a element is next one. So we are going to get this is. So eventually we can say that the left coset is equals to the right coset. So we can say that it is an abelian group. It is an abelian group. So z comma plus is an abelian group. So we can say that a plus e is equals to e plus a, left or right cosets. Now let us go for the another one. So here it is nothing but G is a group which is consisting the modulo operation Z12. Z12 means we are going to consider, so it is up to 12. Up to 12 means it is not equal to 12, less than 12. So we are going to consider the elements such as like this: 0, 1, 2, and so on, 11. It is nothing but Z12 is it is congruent to modulo 12. So we are going to get it is 12. Up to 12 elements will be there, but it is started from 0 because 12 will become 0. 12 will become 0. So I am going to get this is. So the set is consisting only this. And now the subset we have to consider this. So this is also a subgroup. This is also a subgroup under addition. So I am just taking this is the group and this is the subgroup. Now find all the left cosets and obtain the corresponding coset decomposition on H. Coset decomposition on H. Okay, obtain all the left cosets. Left cosets means we have to take each and every element of the set G. So how many elements are there? 0, 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11. So all the elements. So I am taking for every element I am considering from G, and I am going to apply with the element of H. See here, this is I am taking A plus H such that H belongs to H. So what I am going to get? A plus 0, A plus 4, A plus 8. Then what about A? What about equivalence class of A is? Equivalence class of A is it is varying from 0 to 11. It is varying from 0 to 11. Now I am just taking 0 plus H, that is 0 plus 0, 0 plus 4, 0 plus 8 is nothing but the set itself. Now 1 plus H. So 1 plus 0, 1 plus 4, 1 plus 8. So I am just taking like this. Next 2 plus H. Similarly, so whenever if it is exceeds 12, then the corresponding value, if it is 12, then I can take it as 0, and if it is 13, I can take it as minus 12. So it is nothing but 1 I can consider. Like that we have to get all the values. Now H plus 2, 2 plus 0, see here, this is no problem, same as it is, whatever the values we are going to get. And now this is also same values that we have to get. Now here observe this, 4 plus H. So what about this? 0 plus 4 is 4, 4 plus 4 is 8, and 8 plus 4 is 12. 12 modulo 12, this will be 0. This will be 0. And here also, then I am going to 0 plus 5 is 5, 0 plus 5 is 4, 9, and the next 0 plus 8 is 13. So it will become 1. It will become 1. 13 minus 12. So it will become 1. Now, in the same way, the other element I am taking from Z. From Z, which is equals to 8 if I am taking. So 8 plus 0, 8. 8 plus 4 is 12. 12 means it is 0. Then 8 plus 8 is 16. 16 minus 12, it is 4. So like that, we have to calculate all the left cosets. We are finding all the possible left cosets. All the possible left cosets. Now, observe this. These are the possible left cosets. Now, observe this. There are 12 left cosets will be there. There are 12 left cosets. See here, how many elements that we are going to apply. That is nothing but number of elements in Z or nothing but number of elements in Z12. So there are 12 elements will be there. Obviously, we are going to get 12 left cosets. So among these 12 left cosets, some are identical. The first 4 are mutually disjunct, and other are identical. See here, we are going to consider this is these first four, observe here, first 4 are disjunct. Whatever the set that we are going to get, see these are the, one is 048, one is 159, one is 2610, and another one is 3711. So these are the disjunct one. And now observe that the next one is 591, which is equal to this. Next, observe this 7113, so which is equal to this. Now observe 915 is this, 915, so which is this. And this is similar to this one, 915. And now 1137, once again, which will be same to this. So only the 4 are distinct, and the remaining 7, whatever the remaining things are here, observe this, 480, which is equivalent to this, 610, 610, which is equivalent to this. So like that. Only 4 are disjunct. So we can say that. So how many disjunct left cosets will be there? That is nothing but the index of H. So index of H in G is the number of disjunct left cosets. So what are the number of disjunct left cosets? Only 4. Then we are going to write it as 4. So what are they? What are those? So 0 plus H, 1 plus H, 2 plus H, 3 plus H. Then the union, if I am taking, this is the coset decomposition. So of a group. So here, this is just it is like a partition of a set, which will be induced the equivalence classes in the same way. That we are going to get 0, H, 1, and the next this is another 1, 1 plus H, union of 2 plus H, union of this one, which is nothing but the decomposition of this. Now, this is the left cosets. Now, based on the left cosets, there are one more theorem will be there. So that is known as a Lagrange's theorem. So in the what is meant by Lagrange's theorem? So here, if G is a finite group and H is a subgroup of G, then the order of H divides the order of G, divides the order of G, which is known as a Lagrange's theorem, which is known as a Lagrange's theorem. So H is a subgroup of G, then order of H divides order of G, order of H divides order of G, which is known as a Lagrange's theorem. So here, using Lagrange's theorem, we are going to solve some of the problems. So G is a group and H is a subgroup with the subgroups, and H and K are the subgroups. So with the cardinality of G is 660, cardinality of K is 66. So this is, of course, it is given as G, and then it is H is a subset, and of course another subgroup is K. So here it is nothing but 66 is the elements here, and these elements here are 666, then all are not equal, then cardinality of H is given already, so it is nothing but what about this? This is 6G. So what I am going to write, so here cardinality of G is equals to, see here H is a subgroup of G, H is a subgroup of G, then order of H divides order of G, that means order of H divides order of G means order of G by order of H, order of G by order of H. So it is having some quotient. If I am going to divide, order of G with order of H, then we have to get something. So that we are going to represent like this. We are going to represent like this. So it is H into some quotient. H into some quotient. Suppose 2 divides 4 means, so what I am going to get? 2 is 4. So what I am going to, this is a quotient is 2. Then I am going to take it as 4 is equals to 2 into, and this is 2. 4 equals to 2 into 2. See, in the same way, this is order of G. Order of Z is equals to order of H, and next it is going to be divides. Order of H is divides order of G. So completely, so it is nothing but some number quotient. So which is going to be greater than 1, which is going to be greater than 1. So now in the same sense for others also, I am going to write H is also going to be divides with K. Order of K divides, because it is also a subgroup. It is also a subgroup. So I am going to write this as like this. Now I have to just substitute the values here. I am going to get 660 is equals to, see here 660 is equals to, H1 is nothing but this value I am going to get 66 into Q1 Q2. Just combining these two. I am just combining these two. So what is this? H is equals to 666 and next Q2 and of course Q1. Of course Q1. And it is nothing but Q2 Q1 or Q1 Q2 or Q1 Q2 is equals to, then I am going to get it as 10. So it is 660. Then I have to multiply with a tensor. So I am going to get Q1 Q2 is equals to 10. So Q1 Q2 is equals to 10. The possible combinations are either Q1 is equals to 2, Q2 is equals to 5, or Q2 is equals to 2 and Q1 is equals to 5. So these are the possible values. These are the possible values. So just those possible, substitute the possible values. What about the Q1 is? Q1 is equals to either it is 2 or it is 5. So then you have to substitute either it is 2, then the value is this, either it is 5, then the value is this, then the value is this. So here, by using the Lagrange's theorem, that one should calculate what is the order of H, what is the subgroup, and what is the cardinality of the subgroup, and that we are going to find out. By using the Lagrange's theorem. So first of all, we are going to given the 3 conditions are given, 3 subsets are given, and apply the Lagrange's theorem repeatedly. Then we are going to get the cardinality of H. One time, if Q1 is equals to 2, one value, and Q1 is equals to 5, we are going to get the other value. So now, so with this, this is related to the Lagrange's theorem, and because the syllabus is consisting only few topics on this one, so I'm not covering much of the problems on Lagrange's theorem. So I'm just I'm going to conclude this session with this example only. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.